In this lesson, we're going to talk about algorithm performance and complexity with Big O notation. Big O notation is used in mathematics and computer science. In computer science, it's used to indicate the performance or complexity of an algorithm in a worst case scenario. So we are talking about the use of some resource by an algorithm relative to the size of the data that this algorithm acts on. And what we're measuring is the rate of growth of the time taken or number of steps taken by our algorithm with respect to the growth of the input data size. So we could be talking about, when we're talking about the complexity or performance, we might be talking about how many steps our program takes, or how long it takes for the steps to execute, or we might be talking about the amount of memory used by our program, or the amount of disk space used. So there are a lot of different parameters that we could consider, but for the purpose of understanding what Big O notation is, I'll keep referring to number of execution steps, and that's a reasonable measure of the complexity of an algorithm. So we're going to try to learn and understand Big O notation in this lesson by looking at example algorithms and example data sizes and considering how many steps our algorithm would have to take in order to accomplish whatever we want to accomplish on a set of data of a particular size. And then the important bit is then considering, as our data size grows, how quickly do the number of steps we need to take grow. So we're looking at the rate of growth of the algorithm compared to the growth of the data size. That may sound really confusing. That's okay. We're going to look at some examples to try to make it clear. But before we do, let's consider some notation and some vocabulary. So what we have in this chart are the some common Big O notations, and we'll talk about the first four in this lesson. And then we've got the vocabulary, the term that we use to describe this notation. So, and we've got these listed in order from least complex to most complex. And what I mean by that is the rate of growth for the notations at the top of this table is slower. It's smaller than at the bottom of the table. So at the top of the table, we have constant complexity. Constant complexity is noted by Big O of 1. And what constant complexity means is that as our data size grows, the number of steps that our algorithm executes stays the same. It stays constant. So it doesn't matter how many items we have in our data set. We could be looking at 100 items or 1,000 items or 1,000,000 items. Our program will execute the same number of steps no matter how many items are in the collection that our algorithm works on. So we call that constant complexity. Next, we have logarithmic complexity, and this is the hardest one for most people to understand, but we'll look at some examples in this lesson. Logarithmic complexity can start off a bit steep, so the growth from, say, looking at 10 items to 100 items to 1,000 items, that maybe grows steadily, but as we get to larger and larger values, the rate of growth flattens out for logarithmic. And so as our data size grows really large, a logarithmic complexity becomes smaller and smaller and smaller relative to that growth. And we'll see why that happens. Next, we have linear complexity. And if you know anything about algebra, then the term linear might be familiar to you. Linear means that as our data set grows, our algorithm complexity grows at the same rate. So if we have 100 items, it takes 100 steps. If we have 1,000 items, it takes 1,000 steps. If we have 1,000,000 items, it takes 1,000,000 steps. So the number of steps that it takes for our algorithm to execute, to complete, grows at exactly the same rate as the size of our data. That is a linear complexity. Next we have quadratic or polynomial complexity, and we call it quadratic when we characterize it as n squared. So this is big O of n squared, and this indicates generally a nested loop with linear complexity in the outer and the inner loop. So if we multiply those two n's in the outer and inner loop, we get quadratic complexity. We'll see some examples of this. So the way that this grows is quadratic. If we have a data set with 10 items, then it takes us 100 steps. And if we have a data set with 100 items, it takes us 10,000 steps. And as our data set grows, we grow by a magnitude of n squared. So you can see that this starts to grow quite quickly, and we try to avoid a quadratic algorithm if we know that our data size might get really big. And then at the bottom of the table we have exponential complexity, which grows even faster. So exponential complexity, very quickly, our data size doesn't have to get very big, and exponential complexity grows beyond the capabilities of some of our operating constraints. So for example, even a data set with 100 values in it may be inappropriate for an exponentially complex algorithm. Sometimes it can help to look at these complexities on a graph. So in this graph we have our input size and on the horizontal axis, and as that grows we go to the right in our graph, and then we have whatever resource we're measuring. So on this graph it says time. It could be that could be execution time, or it could be number of steps, and this is the complexity growing on the vertical axis. So if we look at constant complexity, we can see it's a flat line. It doesn't matter how much our input size grows or how fast it grows, it's going to take exactly the same amount of time or steps to execute a constant complexity algorithm. It has no dependence on the input size. Next, we can see that logarithmic complexity, while it might start off growing a bit fast, it flattens out over time. So logarithmic complexity is very desirable if we know that our input size is going to grow very large, because the number of steps or time taken by our algorithm will flatten out and get closer to constant complexity over time. It never becomes constant, but it gets flatter and flatter and flatter as, not over time, but as our input size grows. So the next is linear, and we can see that it is a straight diagonal line. So a linear algorithm grows at exactly the same rate. The time taken grows at exactly the same rate as the input size. So if our input size is 100, the time it takes is 100. And if our input size is 1,000, the time it takes is 1,000. It grows linearly. And then we've shown quadratic complexity on this graph, and you can see that it starts to grow really quickly. If we had exponential on this graph, it would be almost a vertical line going up, so it would be much steeper than the quadratic line. So this gives a visual representation of the way that complexity reflects the time, how the time taken grows in relation to the input size, which is what we're measuring with big O notation. So before we go on, let's make sure everybody understands what I mean when I talk about an algorithm. An algorithm is just a sequence of steps that we use to solve a problem. And when we're talking about programming, these are just actual lines of code that we execute in our program. So some examples of algorithms that are really common in computer science and which we use to understand big O notation and complexity are a searching algorithm, which is a set of steps that we use to find a value in a list of values. A counting algorithm is a set of steps that count the instances of one thing in a group of things. And a sorting algorithm is a set of steps to put a set of things in order. So let's look at each one of these complexities more closely with examples. We'll start with constant complexity. So if an algorithm always takes the same number of steps, no matter the size of the input, then we say that it has constant complexity. And an example of that is a function that returns the first element of an array. If we're returning the first element of an array, it doesn't matter how many elements are in that array. It could have 1,000,000 elements, and we're still going to execute the same sequence of steps. So notice that even though we're talking about number of steps and we say big O of 1, it doesn't mean that our function or algorithm can only execute one line of code. It just is really a symbol that indicates we execute the same lines of code no matter what the size of the data. So in this case, in this implementation, we do a check to see if our array is empty or null, and if it is, then we just then we just return null, and otherwise we return the first element. So we have a couple of steps here, maybe 3 steps at most. We do an evaluation. Actually, it's 2 steps. We have an evaluation and then we return a value, but we still consider this constant complexity because we execute these same 2 steps no matter how big our array gets. Next up the ladder is logarithmic complexity, and this one can be the most difficult for people to understand. But you can consider that logarithmic complexity always involves some sort of divide and conquer type of algorithm. Examples of that are binary search or merge sort. So let's talk about binary search as an example. In binary search, we have some loop where we're searching for a value in a list of values, and that list of values is sorted. And we each time through the loop, we cut our data size, our list, in half. So at most, it will require log n steps, where n is the number of items in the input collection. And when we're talking about a binary search where we cut the list in half, that's what binary means. We're cutting it in half each time. We're talking about a log base 2 algorithm. Don't worry if you don't know what that means. We're going to look at an example now to try to make it more clear. Let's use an example to understand logarithmic complexity. So here I have a sorted array, a number array, and we're going to consider binary search, which is a logarithmic algorithm. So we have 10 items in this array. So the length is 10. And let's say that we're looking for a value 7. Let's say we're looking for the value 7 in this array. So I'm just going to write some pseudocode here. So we would do something like, this is the way binary search works. We have a loop, and inside of that loop, the first thing we do is we get the midpoint. So the midpoint of the array is the length of the current array we're looking at divided by 2. And we'll just keep it simple and say that's what it is. Then we get the value at that midpoint. So the element we say is the array at that midpoint. And then we do a check and we say if value, that's the thing we're searching for here, if value equals element, then we return it. And maybe we return the value, or maybe we return the index. Let's just say we return the value. Otherwise, we say if the value is less than the element, well, then we know that our value is somewhere to the left of where we currently are. So we'll disregard the right of the array after this point. So we'll discard the upper part of the array. And else if the value is greater than the element, then we know we can discard the lower half of this array. Okay, so let's think about if we had a value 7, then the first time we come into this loop, we set a midpoint. So let's say that we set a midpoint of length is 10 divided by 2 is 5. So that's our midpoint index, 5, which is right here. And then we check to see what element is. Element at index 5 is 32. So then we check to see, is value equal to element? Value is 7. Is 7 equal to element? No, it's less than that. So we discard everything from this index to the top of the array. We discard that. We know our value is not there, and we go back up to the top of the loop. Now we go back up to the top of the loop, and now we're just dealing with this lower part of our array. So we have a new length. We have a new length now. It's only 1, 2, 3, 4, 5 elements. So we have half as many elements the second time through. And we'll set a new midpoint. So our new midpoint is 5 divided by 2. If we just do integer division and take the floor, we'll say that that's 2. And so our value at index 2 is 6. And then we check again. We say, does 7 equal 6? It doesn't. This time it's greater, so we're going to discard everything from this index down to the start of the array. And then we start over again. So now we have the array that's left is only length 2. The midpoint, 2 divided by 2 is 1, so we'll set a new endpoint of 1. Well, at the first index of this subarray that we have here, we have the value 15. So we check and we see that value is less than that. So then we discard the 15 and we're left with the 7. So we're done after these 3 steps. Well, 4 steps. It took us 4 steps because the last step is where we find the 7. So it took us 4 steps. Now, the reason that we call this logarithmic is because we are splitting the list in half each time. Each time through the loop, we'll have half as many items to consider. So if we consider that if we have 10 items and we think about what power of 2, what's the minimum power of 2 to get 10 items, guess what it is? It's 4. It's 4. So 2 to the 4th is 16. And 16 is the smallest power of 2. That's at least 10. Now, if we had, let's consider a case that we had 100 values. So our length is 100. Let's look at the worst case to find a value we're looking for. So if the length is 100, the first time through, we'll cut it in half and we'll have 50. The second time through, we'll have 25. The third time through, we'll have 13. The fourth time through, 7. The fifth time through, 4. The sixth time through, 2. And the seventh time through, we're left with our 1 item left. So guess what power of 2 we need to get a value that's at least 100? You guessed it, it's 7. So this is happening, of course, because each time we're splitting our list in half. That's why the max number of steps is the power of 2. That gives us at least that number. So now what if we had 1,000 values? Well, 2 to the 10 is 1024. So at worst, it will take us 10 steps to process 1,000 values. So you can see at the start here, as we increase by a power of 10, we're increasing how many steps by a constant number, by 3. We have to do 3 more steps for each increase. But once we get up to something much larger, like let's say we had 1 million is our length, well then let me work it out on the calculator. What power of 2 gives us at least 1 million? That happens to be 2 to the 20th. So 2 to the 20th gives us 1,048,576. So 20 steps max to get a million, to deal with an array with 1,000,000 values. That's only 10 more steps than if we had 1,000 values. So what you'll see if you graphed this is you'll see that we have something that looks like it grows a bit constantly at first and then it levels out. So this is the characteristics of a logarithmic algorithm. And here when we're talking about a binary search algorithm or something like a merge sort where we split the list in 2 each time, we end up with a logarithm base 2 algorithm like we see here. And you can see from this the benefit. If we had a 1,000,000 length array and we processed it linearly, and then it would take 1,000,000 steps to go through every element of the array. So 20 steps is a lot better than 1,000,000, isn't it? So hopefully that makes logarithmic complexity a bit more clear. The key things to take away are that we have logarithmic complexity when our algorithm does some sort of division of our data set and discards part of our data set through each iteration. Next, let's talk about linear complexity. A linear algorithm requires as many steps as there are values in the input data set in the worst case. Another way to think about it is that as our data size grows, our algorithm requires the same increase in the number of steps. So as the pieces of data grow, the number of steps grows at the same rate. So an example of that is a counting algorithm. So if, for example, we wanted to count the occurrences of a value in a certain collection, we would pass that array into our function along with the value we're searching for. And because we want to count how many times that value occurs in the array, we have to look at every element in the array. So if the array has 10 values, we're going to look at 10 values. And if the array has 100 values, we're going to look at 100 values. And if it has 1,000,000, we're going to look at 1,000,000. So the number of steps required to execute this algorithm is directly related to the number of values in the data set. And oftentimes, we consider it equal if we consider one step through this loop as a single execution step. So it's what matters here is that the number of steps increases at the same rate as the number of values increases in our data set. Now let's talk about quadratic or polynomial. So quadratic is O(n) squared, and we typically find this in a nested loop, and specifically in a nested loop where the outer loop is linear complexity and the inner loop is at linear complexity. So we have n times n complexity, which is n squared. One example of this is a bubble sort algorithm. So in a bubble sort algorithm, we have typically an outer while loop that executes until we have gone all the way through the array and there are no more items to swap. In the inner loop, we look at each element of the array, and if we're sorting in ascending order, then we check to see, is this item bigger than the next item? If it is, swap them. So each iteration of the inner loop looks at each element of the array. So that's linear complexity on this inner loop. You can see we go from 0 to the length of the array minus 1. So this inner loop is obviously executing n times if our length is n. Now in a worst case scenario, we will have to swap every element in the array, which means we'll have to make, if our array is length n, we'll have to make n passes of this inner loop in order to get everything sorted, which means this outer loop, this while loop, will also execute n times in a worst case scenario. So we have a linear outer loop and a linear inner loop. For every For every time in the n times in the outer loop, we'll execute n times in the inner loop. That's n times n, which is O(n) squared, or quadratic. Let's look at an example to see if it makes it more clear. In this example, we will consider searching for all the elements in one array in another array. So here we have two numeric arrays. I've made them small so that this example doesn't go on too long. And these arrays are not sorted. So let's say we have a situation where we have two arrays and they're not sorted, or we don't know if they are. And what we want is to return a new array. So return an array of the intersection. So the intersection, we'll remember from sets, are the elements that are common to both of these arrays. So that means for each element in A, check to see if it's in B. Right? And if we find that the element in A is also in B, then we'll return it in the intersection. So the pseudocode will look something like, we'll have a loop through A. So this will go from, A dot length times, right? Because we'll look at every element in A. And then for each element in A, we'll loop through B. So that's going to go B dot length times. And we'll check to see if element A equals element B, then we'll add it to the result. Right? So it'll look something like this. And so if our length of the two arrays is n, then what we have here is n times n, because for every iteration of the outer loop, we execute the inner loop, we execute the outer loop n times, we execute the inner loop n times, so we have n squared complexity. Now, what if we knew that array B was sorted? So what if B is sorted? What could we do then? Could we improve our order of n squared? Well, we could, because if B is sorted, our algorithm changes to something like this. We still have to loop through all the elements in A. Loop through A, so we still have A dot length on the outside. But inside, we could perform a binary search on B with the element from A. Right? And we also know that this is going to be a loop, but what is the complexity of this binary search? Well, it's going to be log n, isn't it? We just learned about that. So now what we have is n for the outer loop and log n for the inner loop. So if we multiply those together, we get big O of n log n. Now, n log n will take longer than a linear. It grows faster than a linear complexity, but not nearly as fast as a quadratic complexity. So remember that our n is going to kind of go up at a steady rate as our data size grows. The logarithm component will add a little bit of a jump to the start of it, but since it evens itself out, it approaches being linear. So don't worry if that's confusing. What's important to understand is that number one, just because we have a nested loop does not mean we have quadratic complexity. If we have a nested loop and we have linear complexity on the outside and the inside, then we have quadratic complexity. But if we have a nested loop and the inner loop is logarithmic, then we improve the complexity to n log n, which is slightly worse than linear, much better than quadratic. Let's talk about exponential complexity. So the best example of exponential complexity algorithms are recursive algorithms that call themselves multiple times. So if we have a recursive algorithm, a recursive function that calls itself more than once inside of that function, then we'll end up with exponential complexity. In general, we really want to avoid this because if our number gets to be even slightly large, then we run into problems. It just consumes too much stack, generally too much memory to execute the program, and we can have a look at why this happens. So the classic example is a recursive implementation of the Fibonacci function. So this Fibonacci function takes a number as input and returns that value in the Fibonacci sequence, that position in the value at that position in the Fibonacci sequence. So a classic way that you might see this implemented is with a recursive function that calls itself with the number -2 plus number -1 until we reach 1, in which case we just return 1. So this seems harmless, but if you try to run this with a number even as big as 100, it will probably crash. So let's have a look at why that's true. Let's see what happens when we try to hand simulate the Fibonacci function for a number like 5. So if we call fib with 5, that seems like a pretty small number. This is what's going to happen. We come in and we say, is num less than or equal to 1? Nope. Okay, then we're going to call Fibonacci with 3 and add it to Fibonacci 4. So this call results in 2 more calls. So let's go down the 3 side. When we call Fibonacci with 3, well, num still isn't less than or equal to 1, so we call Fibonacci with 1, and we add to it Fibonacci of 2. So it makes these 2 calls. Now Fibonacci of 1 just returns 1, so we're done there. But Fibonacci of 2, we'll call Fibonacci of 0 plus Fibonacci of 1. Now, each one of these will return their numbers. Now we go over to the right side and we have Fibonacci of 4. Well, that's going to call Fibonacci with 2 and add to it Fibonacci with 3. And this one is going to call Fibonacci with 0 and add Fibonacci with 1. And this will return 0 and 1. But this Fibonacci of 3 will call Fibonacci with 1 and Fibonacci with 2. This one will return 1, but this Fibonacci of 2 will call Fibonacci with 0 and add Fibonacci with 1, which will return 0 and 1. And we add up all of these numbers and we get the answer. But look at how many times we've called this function. So let's look at how many steps it requires. For 5, we have 1, change my pen color, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it took us 14 steps for the number 5. What if we called it with 6? Well, if we called it with 6, we would call it with 5, so we'd get all of this 14, plus we would call it with 4, and we'd add those together, right? So we get this 14 plus all the steps from 4, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would give us our 14 plus 9, so that takes us 23 steps. Now just imagine if we did that with 100. So we can see that this, the rate of change in the number of steps we have to execute grows really quickly as the size of our number gets bigger. So this is why if we try to put in a value of 100, it'll crash our machine. So just as a review, exponential algorithms occur most commonly when we have a recursive function that calls itself more than once. Don't do that. One more thing we'll talk about is just to make sure that we have a sense of calculating big O notation. So this is like the example that we just saw for quadratic complexity, but let's just look at it again. Make sure we understand the questions to ask so that we can calculate the big O complexity. So if we look at this code on the screen, we have two arrays, and the size of each array is 4. And we're searching in array 2 for each value in array 1. So then we see that we have a nested loop. In the outer loop, we're looking through array 1, and the inner loop, we're looking through array 2. So if we ask ourselves, how many times will we go through the inner loop in a worst case? So that's this loop here. Well, since we're looking at each value of array 2, then in worst case, we'll look at 4 values. And then we ask, how many times will we go through the outer loop, this loop here? Once again, array 1 has 4 values, so if we look at each value in array 1, then we'll go through it 4 times. We multiply those two values, 4 times 4, and we get 16. N times n, and we get n squared. So we can see that the complexity of this algorithm is O(n) squared, or quadratic. Let's look at one more example of calculating complexity. So let's consider our case again, that we have these two arrays and we're trying to find the intersection of those arrays. So we know from before that if we do it the traditional way with a nested loop, we'll have quadratic complexity. So we'll get O(n) squared complexity with a nested loop. So we also saw that if we knew that one of these arrays was sorted, then we could take advantage of binary search and reduce our complexity to n log n. So what would it take if we used merge sort to sort B? So if we sort B with merge sort first, and then we do a binary search of B for each element in A. Then we could accomplish our n log n for step 2. We know that for this step we can get n log n because for each element in A we'll do a binary search in B and we'll get n log n. But what about this first step, sorting B with merge sort? Well, I'll tell you that merge sort has a complexity of n log n. That's the complexity of merge sort, and you can do some research to find out why that's the case. So if I do this step first, our code would look something like merge sort B, and we would perform that step, right? We would say something like sorted B equals merge sort B. And this step would take O(n) log n. Then we would intersect A and B. And we know that that step also takes n log n. So we'd say something like intersection equals intersect A and sorted B. And we know from the last example that this also takes big O of n log n. So now instead of multiplying these two, we perform this step first and this step second. So we add these two complexities together. So the total complexity is n log n plus n log n. And that is 2 times n log n. Now, another thing to note about complexities is that we ignore any constant values that are multiplied by the overall complexity. We just ignore that, because for very large values of n, which is generally what we're interested in, that number becomes less and less and less significant as n grows. So even though our overall complexity is 2n log n, we still say that the overall complexity is n log n. So by this example, we can see that if we have 2 unsorted arrays, even if we sort one of the arrays first with a merge sort, we still will end up with our n log n overall complexity.